MIXAL, or mixed assembly language, is a symbolic language used to make mixed programs considerably easier to read and to write. It's an extension of the instructions that we covered in the last presentation. Its main features are the optional use of alphabetic names to stand for numbers, and a location name to associate names with memory locations. The mixed assembler reads MIXAL files line by line, produces binary instructions, which are associated to predefined memory addresses. In addition to mixed instructions, you can include in MIXAL file assembly directives. These are addressed to the assembler itself, for example, telling it where the program starts and ends, or to reposition the location count. Mixed instructions and assembler directives are written in MIXAL, one per source line file, according to the pattern seen here. Knuth's listings also include a line number, and he makes reference to the number of times an instruction is executed. Furthermore, he calls the label portion location, but it is the same. Let's take a look at an example. This is the find maximum algorithm. Given n elements x1, x2 through xn, we will find m and j such that m is equal to x of j and is equal to the max of x sub I, where j is the largest index that satisfies the relation. In analyzing this algorithm, we require a fixed amount of storage, so it's only necessary to look at the time required to perform it. We also know from past experience that the number of comparisons is O of n. But what about the number of assignments? To get this information on the number of assignments, we can look at the number of times each step is executed. We'll also see how this information can help us with seeing how long it takes on a particular computer. Here we know everything except A, which is the number of times that we need to change the value of the current maximum. As with other algorithms, we're interested in the best, average, and worst cases. The minimum value for A is 0, which happens if xn is the highest value, since that is the one we set initially. In this case, no more assignments are necessary. The maximum value is n-1, which happens when the list goes from greatest to least. x1 is greater than x2, is greater than x3, all the way out to x to the n. So our average is going to lie somewhere between 0 and n-1. To determine the average, we need to make some assumptions about the data. We assume that we have all distinct values and that each of the n factorial permutations of these values are equally likely. And again, note the performance of the algorithm does not depend on a precise value of x sub k, only the relative order involved. Here, the average of A is equal to 5/6. We can use our knowledge of permutations to show that the probability that A has value k will be the number of permutations of n objects for which A is equal to k divided by n factorial. We call this value p sub nk. From here we can calculate the value in the usual way. We can calculate the variance and the standard deviation as well. Now let's take a look at how to implement this algorithm in MIXAL. This program is your old pal findmax translated into MIXAL. The columns labeled loc, op, and address contain the program in MIXAL symbolic machine language. The column labeled assembled instructions shows the actual numeric machine language associated with the MIXAL program. Knuth also includes the line number. It's not an essential part of the program, but makes it easier to find parts of the program. Remarks gives explanatory information about the program and allow us to compare the code with the written algorithm. Knuth also states the register assignments here. There's a little bit of programmer's license since command M2 is given at the end of the loop rather than at the beginning, as was the case with the algorithm. Times indicates the number of times the instruction gets executed during the course of the program. We can see that line 6 will be performed n-1 times, for example. With our timing information from the last presentation, totaling the time to perform this would be 5 plus 5n plus 3a, where a is the number of assignments and n is the number of items. In terms of the program, line 1 tells us the symbol x is equivalent to the number 1000. Line 2 says the locations for succeeding lines should be chosen sequentially beginning at 3000. The symbol maximum that appears in the loc field of line 3 becomes equivalent to 3000, and it is 3001, etc. Lines 1 and 2 have EQ and ORIG. These are pseudo operations. They only talk about program M rather than indicating the name variables for the program, or requiring any assembly. That is why there are no assembled instructions associated with these lines. On lines 3 through 12, the OP field contains the symbolic name of the mixed instructions. Line 3 is the store J instruction that stores the contents of register J into the 02 field of the location exit. The rest of the program is fairly self-explanatory according to the algorithm, although line 7 has some new notation. An asterisk is interpreted as self, so star plus 3 refers to 3 locations past the current line. Line 12 also uses this notation. The net effect of this program is that we initialize the variables first. Next, we determine whether x sub k is less than or equal to the maximum. If it is, we decrease k and check to see if they are all tested. If xk is greater than the maximum, we set the maximum to XK and check to see if we have tested everything in the array. Mix is a mythical computer and MIXAL is a mythical computing language. The primary benefit to knowing MIXAL is to understand the details of the algorithms developed in Knuth's text. For example, knowing the types and timing of operations can help us to get a handle on the average computational complexity for an algorithm. Sometimes it's useful to implement algorithms in MIXAL. This is helpful if we want to make sure that we have specified an algorithm correctly. There are a wide variety of mixed development platforms out there. GNU has the GNU MDK, which includes quite a few development features and is linked here in this slide. GNU's Kit has the assembler and a virtual machine on which to run your programs. The virtual machine also has a graphical user interface. Running programs allows you to better understand how the algorithms work, since you can check the registers, flags, and memory contents at each step. You can also simulate the input-output devices using standard I/O. Finally, you can collect timing statistics. The 4 presentations in this module relate to Mix and MIXAL, and they cover approximately 20% of the content of the first volume of Knuth. As stated at the beginning of this adventure, the purpose of this portion of the module is to give you knowledge of how to read Knuth's text, rather than to make you fluent in MIXAL. There's a lot more to these texts, and I would encourage you to take a look at them, or maybe even purchase them for your library. Thank you as always for watching and going on this adventure.